So, are we online? Okay. So, we're sorry about we are late, right? But we have had issues. So, thank you very much for waiting. We are back. We are back for the third class, third lecture. I have some forms. First of all, we will upload. I don't know if we have had or if we will, but we are going to upload the lecture notes on the mini course website, so it will be available for you. And the second form is that now you are able to make comments and make questions in the chat. So you can make questions about the previous lectures or about this one, as you prefer. And thank you very much, Professor, and we can start.
Okay, I hope I'm audible. Okay, so today I will discuss the Baryon asymmetry of the universe. So let me start with the evidences which we know about. So there are several evidences which tells us that there is baryons, not antibaryons. Okay, so why do we care about antibaryons? Because Paul Dirac taught us actually that there should be antimatter for every matter, and that he actually first hypothesized to actually solve the negative energy problem in the quantum field theory of Dirac fermion. And subsequently Anderson discovered positron, and after that we have been discovering antimatter anyway. So antimatter, the issue with antimatter is that we can create it artificially in our laboratory, but we do not see too many natural sources which actually gives us antimatter. It gives mostly matter. Okay, for example, if we care about the evidences, direct evidences, so first of all we can look at, say, cosmic rays. Cosmic rays are basically very highly energetic particles, mostly protons, which are coming from very far away distances. We can detect them in different experiments. They mostly contain matter. They have negligible antimatter. I'll call antibaryon. So B is just for baryon, okay, just for the short. And you can also have other indirect evidences. For example, if there are baryons and antibaryons in the universe, what they will do, we all know that matter can go to radiation, radiation can go to matter. So baryon and antibaryon will come together, and it will give you, so B and B bar, it will come, let's say it's a fermion, it will give you photons, okay? And these photons are monochromatic photons because it's just the mass of the baryon, basically, right? So you will see too many monochromatic gamma rays in the sky if you have equal amount of baryons and antibaryons in our universe, okay? And there are very tight limits on monochromatic photons in the sky because we don't have too many sources of them. All we see, the photons are basically diffuse, okay? So we don't see that, okay? So that tells us that baryons are not finding antibaryons to annihilate into gamma rays, right? You can also go on, you can look at light nuclei abundance, which is called BBN. So BBN, we know that initially we had quarks and all the fundamental particles, then quarks form neutrons and protons, and then as the temperature gets lower and lower, protons and neutrons, they can combine and they can form, say, deuterium. Then you put one more neutron, it will form tritium. You put proton plus neutron, it will form helium. Some amount of lithium also, but by then the universe has already become cold, so, and less dense, so you cannot fuse helium and produce carbon or something like that. So you stop at that, but that is good enough for us because the theory, lambda CDM, tells us how much of helium should be there compared to hydrogen in our universe. You measure them from different astrophysical sources, and that actually agrees well with the theoretical predictions and all the calculations in BBN. It assumes that there is only baryon, there's no antibaryon, because if you put antibaryons also during the nucleosynthesis, which is happening at, say, time of the order of temperature of the order of mega electron volts, or if you look at time, a few seconds, say first few minutes or minutes. 1 minute, okay? After the Big Bang. So when this is happening, if you put antibaryons, what will happen is that baryons and antibaryons will keep annihilating for a long, long time, okay? And if you want to have this nucleosynthesis, you want things to go out of equilibrium, okay? So that is actually tells you that during the time of nucleosynthesis, at least, you should not have too many antibaryons. Otherwise, you will be forming anti-helium also, anti-deuterium also, which you should have seen today, okay? but you don't see them. Okay, so that is another one. You can also have evidence from CMB. CMB is happening even at a lower scale, T of the order of electron volt, time of the order of 380,000 years. And if you look at the CMB peak, which I discussed yesterday, it's like this. So if you put more baryons, so this is actually observed, and you can calculate it from the theory by assuming certain amount, because these peaks are very sensitive to how much baryon you put. So if you put more baryons, obviously you have the photons will find it more difficult to come out of the region which is more baryons, because photons directly interact with the baryons. So you will see more fluctuations, more cold and more hot spots in the CMB. So if you put more baryons, it will just go up like this. Okay, so it actually puts a constraint. So both these things, all these things are actually consistent if you have baryon density minus anti-baryon density over density of photon of the order of 10 to the power minus 10. It is a small number, but it is conveniently represented in this form because we precisely know what is the number density of gamma. Okay, so since there are so many photons in the universe, like 400 per centimeter cube, that's why this number looks very small. Okay, but what is important is that it's non-zero. Okay, so now how to create baryon asymmetry? Okay, so how to create it? How to create BAU? We can ask first, like, why do we even care how to create BAU? Okay, let's start with a BAU. Let's start with a universe which has non-zero baryon asymmetry. Is there a problem with that? The problem is that if you start with, so that's like initial condition. So start with an initial delta B, or this guy is called eta B. Let's say start with initial eta B, which is not equal to 0. Okay? It looks extremely fine-tuned to us as a theorist, but practically also the problem is that if you start with a non-zero eta B, we all know that the universe had gone through an accelerated phase of expansion during inflation, and inflation dilutes everything. Okay? So even if you start with some value, it will be almost, because inflation expands our universe by exponential to the power 60 or 55, so anything that you start with, it will get diluted. Okay, so you cannot have, so this is extremely unnatural to start with this kind of initial conditions where you have a very precise and excess of baryons over antibaryons at t equal to 0 or where t very small, but it will be anyway diluted by inflation. So we don't think of it as a good solution. So that means that what is more natural is that you start with, so this is going to be diluted by inflation anyway. So the next solution, or the only solution, is that you produce it. So start with eta B equal to 0 and create eta B not equal to 0 dynamically. Right? That means with the evolution of time, you do something which will actually create eta B not equal to 0, but starting with eta B equal to 0. Okay? So to do that, there are certain conditions which needs to be satisfied. So that brings us to something called Sakharov's conditions. So Sakharov, as early as 1967, told us what are the conditions that have to be satisfied in order to create baryon asymmetry dynamically in the universe. Okay, so they are, so first one is B violation, which is obvious because you had B equal to 0 initially because you have equal, mind you, the baryon number of proton is 1, baryon number of antiproton is -1. So if you put equal number of baryons and antibaryons, the net baryon number of the universe is 0. So if you start with B equal to 0, and then with time you have B non-zero, obviously you are doing something which violates B. Okay, that is clear. Something which is not trivial, not slightly non-trivial, is that you need both C and CP violation. C violation is obvious because C takes a particle to the antiparticle. So if you say that, okay, I want to create more proton, less antiproton, obviously you are violating C. But CP is slightly bit subtle. So if you violate C but preserve CP, that is also problematic. It is problematic in the sense that so you have C violation, but no CP violation. Then what will happen? Your rates, so let's say you have a particle A, which is going into, or let's say you have a particle X, which is going to Y plus B. So B has a baryon number, okay? So you can also have X bar going to Y plus B bar. So this process is going to create baryon number 1, let's say. This process is going to create baryon number -1, right? So if you have these processes with C violation, what it means that this is not equal to this. So if this is not equal to this means that there is C violation. Now CP, when you have CP, because this is parity, then you have to look at the chirality or the helicity of the particle, okay? So in this case, so let me write down the helicity explicitly. So let's say X goes to left-handed quarks like this, which should be equal to, because CP will transform these guys to bar and right-handed, right? So this is equal to X bar going to QR bar, QR bar. Similarly, if I find out X going to QR, QR, it will be equal to X bar going to QL bar, QL bar, right? What is the problem with that? Then you will find that X going to QL, QL minus X bar going to QL bar, QL bar is equal to X bar going to QR bar, QR bar minus X going to QR, QR. Okay? So you write this term, you write one more term where X goes to QR, QR is equal to X bar goes to QL bar, QL bar. Take the difference of these two equations, you will get these equations. Now what is the problem with these equations? These equations tells you that the left sector asymmetry, this is the left sector, is equal and opposite to the right sector asymmetry. Because asymmetry we define as X going to something minus X bar going to something, okay? So X going to something minus X bar going to something, this is the left sector asymmetry. And here you see that there's a minus sign, you can put a bracket, and you find that X going to right sector minus X bar going to right bar is equal and opposite. So whatever you have in the left sector will be just cancelled out by the right sector. So net asymmetry is 0, okay? So that's why you need both C and CP violation, okay? And the last one is the departure from equilibrium. Why do you want to do that? Because as I mentioned yesterday also, if you maintain equilibrium, there is no difference between forward and backward direction. So if you start with, so there is no arrow of time if you always maintain equilibrium, because forward and backward are basically same. So if you start with B equal to 0, it will always remain B equal to 0. So if you have to go beyond the equilibrium to actually get B not 0, starting with B equal to 0. Okay? So these three conditions one has to satisfy in order to create non-zero baryon asymmetry. Okay? All right. So now the question is that can we do that in the standard model? Okay? We'll find that we cannot do that in the standard model. Let's ask this question whether we can have these things, all these criteria satisfied in the standard model or not. In the standard model, do you have B violation? We have B violation, not at the renormalizable level, but if you go to non-perturbative level. For example, when you say something is conserved, how do you define those things? You define those things as is equal to 0. So this tells you that J mu is a conserved current. Okay? Now what turns out that baryon number and lepton number, they are actually found to be conserved in the standard model, but we do not know why they are conserved. That's why we say that they are accidental symmetries, and they are found to be conserved at all orders of the perturbation theory. But the problem is that if we, so these are symmetries which are exact at the classical level. Okay? So if you go to quantum level, there is something called triangle anomalies. So what they will give you, del mu, J mu, del mu, J mu be not equal to 0. So this is called anomaly. Okay, so these currents are called anomalous because they are conserved at the classical level, but if you go to quantum corrections, they are not conserved. So what we find is that del mu J B plus L in the standard model is non-zero, but B minus L is conserved. That means whatever we get on the right-hand side for the baryon number, we get the same thing for the JL mu also. So that if you take B minus L, it's 0, but if I take B plus L, it is not 0. Okay? But there is no perturbative particle physics analog to describe this kind of processes. These are non-perturbative processes. These are like instanton type solutions. So instanton is like a classical solution of your field equation. So if you do that, you will find that is some energy and you get some kind of degenerate vacuum for the classical field equations, and you can stay in any of the minima. Okay, so these minimas are basically quantified in terms of something called Chern-Simons number. So this is like a topological invariant quantity. So if you are here, if you go to here, what changes? NCS changes, and NCS is actually related to the baryon plus lepton number. So if you start with B plus L equal to 0, if you can manage to tunnel into this vacuum, everything is same. Only thing is that B plus L will change, that's all. So you can go to some other B plus L. So these tunneling solutions are called sphalerons. But the problem is that if you calculate what is the tunneling rate of going from this to this, is very small. It comes out to be the amplitude of tunneling is e to the power minus 8 pi square by z square, which is 10 to the power minus 173. It's very small at T equal to 0. Temperature equal to 0. But if you go to high temperature, what happens? Tunneling rate may be small, but it can climb because it has so much of thermal energy that it can actually climb. It doesn't have to tunnel. So that was actually pointed by these people like Kuzmin, Rubakov, Sapoznikov, and all. So they actually showed that these tunneling solutions or sphalerons, they can be in equilibrium if you go to very high temperature. So for example, if you go to 10 to the power 2 GeV, and if you are in this regime, they are very active. So they are in equilibrium. That means they are going across the barriers, both directions. It can increase, it can decrease, okay? So they are going on. So in principle, you can now say that, okay, I can have in the early universe, I can have baryon number violation even in the standard model, okay? So that actually led people to think of like what could be the way of producing a baryon asymmetry in the standard model. So that actually people thought that there can be something like an electroic baryogenesis. Because I told you earlier that we have seen CP violation in the standard model. C is anyway explicitly violated in the standard model. So C and CP violation is already happening. And the departure from thermal equilibrium is also going to happen at some point because the universe is expanding, temperature is going down. So that actually makes the sphalerons also go out of equilibrium at some point, right? Because if you go below 10 to the power 2 GeV, sphalerons go out of equilibrium, okay? So it's fine. Everything is fine. Now we have to compute and see whether it is going to work or not, okay? So that's what people did. But to have electroic baryogenesis just with the standard model, you need to satisfy another criteria, which is actually related to this departure from thermal equilibrium, is that you need something called the first order phase transition. First order phase transition, which I call FOPT. So you find out the Higgs potential. For example, the Higgs potential as a function of phi, we know that it is like a Mexican hat at t equal to 0. If you look at, so this is say t equal to 0 right now. If you go to high scale, I know that this is just a parabola. What happens in between? That is a model-dependent statement. You have to write down the potential, including the Coleman-Weinberg and the finite temperature corrections, and you can vary the temperature and see how the potential shape is actually changing. If you find a temperature in between, which looks like this, where the potential looks like this, it means that you have two degenerate minima, okay? T equal to Tc, the critical temperature. So this is called the first order phase transition. This is like the boiling water. If you boil water, you form bubbles. So bubbles actually separates two vacuum. One is outside, one is inside. Outside is the water, inside is the air. Air is the true vacuum because at that time you have already heated up to a temperature where air should be the correct vacuum, but there are water also, right? So these two, one is air and one is water, that actually tells you there are two minima and they are separated by a barrier, which is a wall. Okay, so it will create bubbles where you say V not equal to 0, V not equal to 0, outside V equal to 0. And bubbles will be growing because that's how it releases all the energy. Because this is going down now. Once you fall below the critical temperature, because temperature is going down, it is going to fall, then this energy is more. So this energy will go there. So you are releasing the latent heat. Okay, so in that process, these bubbles will grow. Now what happens? So if you look at the bubble wall, so let's say this is the wall. This side is equal V not equal to 0. This side is V equal to 0. So wall is going along this direction because it is actually expanding with some velocity, say VW. So if you look at the quarks, so say QL, it will come, it will hit, some amount of it will go inside, some amount of it will go in the backward direction. Okay, similarly, you can have QR will come, some amount will go in this direction, and some amount of will go in this direction. Same you can do for Q bar also. Q bar. Okay? So in this process, what you do, you actually produce some asymmetry, some CP asymmetry. So the CP asymmetry I have already mentioned, you make some difference between this and this. Okay? Because the amount of QL which is going inside and QL bar which is going inside, they need not be same. Okay? So there is CP violation. So this wall, how these guys interact with the wall, you can think of it like the quarks are interacting with the Higgs field. We write down the term like Q bar, H, UR, Q bar, H tilde, DR, and all these things. So that is going to tell you how these guys are going to interact. So you need CP violation at the wall, which you can try to relate with the CP violation in the CKM or in the quark sector, the Higgs coupling with the quarks, okay? So you are creating some kind of CP asymmetry near the wall, like this. And if you have a CP asymmetry, the sphalerons, because the sphalerons are active here, they're very active, because here the V equal to 0. If the V is not 0, the barrier height increases. So the barrier height is actually proportional to the V. So if you have V non-zero, the sphalerons find that the barrier is too high, I cannot climb. But here V is non-zero, so sphalerons keep going. Okay, there's no problem. So sphalerons are very fast here. So what it will do, the sphalerons will actually create, so this is for say delta Cp, and this is say delta B. So sphalerons will create some baryon asymmetry outside the wall. Okay, and then what happens, since the wall is going in this direction, some amount of this baryon asymmetry will try to diffuse inside the wall. And we want it because inside the wall is a true vacuum. We live inside the wall, and wall is expanding, and it will actually cover the entire universe, right? So this is the typical scenario of electroweak baryogenesis. So what we want sufficient CP violation of this quark interaction or Laplace interaction with the wall, so that you can create the required CP asymmetry, and also you want a first order phase transition. And problem is that the CKM CP violation is too small. So these are the problems, and the problem is that for Higgs mass 125 GeV, FOPT not possible. For the electroweak phase transition to be of first order, you need the Higgs mass to be below 65 GeV. Okay, so which is not. We have already seen that the Higgs mass is 125. Okay, so you cannot do that. So this is actually important to understand why it is not possible. So before going to beyond standard model, we should always be sure that in the model which we have understood so well in last few decades is actually not going to work to create a baryon asymmetry dynamically. Okay, so that actually motivates us to go for beyond standard model. So what we need in the beyond standard model, if you want to follow this route, electroweak baryogenesis, you need to make sure that your electroweak phase transition is first order, which is not possible with just one Higgs. So you can add more scalars, make the electroweak phase transition first order. You also ensure that there is more CP violation compared to the CKM CP violation. That will make sure electric baryogenesis will work. Okay? I am not going to talk about electric baryogenesis. I'll talk about leptogenesis because it is actually connected to the neutrino mass, which I mentioned earlier. There are many other models. There's something called gut baryogenesis, ground unified theories. Because ground unified theories violate baryon number naturally, because people actually propose ground unified theories to explain why proton does not decay. They wanted proton to decay, so they proposed all those theories. But they are very non-minimal, and of course there are many motivations, but I'm not going to talk about it. I'll talk about just simple type 1 seesaw, which we discussed, and it's a very minimal model, just add right and neutrinos, it does everything. Okay?
I have a question. How that violation is created?
Which one?
Both of them.
Which one?
In the right side, below?
This?
Yeah.
Yeah?
How is this created?
This one?
Yeah.
This one is created because you want to ensure that your QL and QL bar, and so you want to ensure that your CP is violated. That means this rate and this rate are different. So QL is going inside, QL is getting reflected, QR is going inside, they are getting reflected. So initially, both QL and QR are in equilibrium, so it's fine. But now, some amount of it is going inside, some is getting reflected. So you are creating an imbalance between these two. Number of QL, number of QR bar. So if you have an imbalance between QL and QR bar, both inside and outside, there will be a CP asymmetry. That's what CP asymmetry means. Mm-hmm. But your net CP asymmetry is 0 anyway, because you see this is plus, minus. So if you include both the sides, net CP asymmetry is 0, which is fine. But the sphalerons are very different on this side and this side. So this will get converted, but this will not get converted. That's the idea.
Okay, great, thank you.
All right, so I'll talk about leptogenesis, because many of the things related to the leptogenesis we have already learned in the neutrino part. So here what happens, you create an asymmetry in the lepton sector. So if you create an asymmetry in the lepton sector, what sphalerons will do, because sphalerons violate B plus L. So let's say you start with B plus L is equal to 1. Let's say L is equal to 1, B is equal to 0, but B plus L is 1. What sphalerun will do? The sphalerun will also take you to say B plus L 2. Let's say you start with B plus L equal to 1, B is equal to 0. There is no baryon asymmetry to begin with. There is lepton asymmetry. Sphalerun can take you to say B plus L is equal to 2. You have to keep in mind that sphalerons cannot change B minus L. So here B minus L was what? B minus L was minus 1. Here also it has to be minus 1. So can you rearrange B and L such that you still have minus 1 but you still get B plus L equal to 2? You can. So that means you are going from B equal to 0 to B not 0. That's the idea. So that means, and only constraint you have this, that you have to create those lepton asymmetry before 10 to the power 2 GeV. Because after 10 to the power 2 GeV, as I mentioned, sphalerons will go out of equilibrium. Sphalerons cannot climb over the barrier to take you from one B plus L to another B plus L. Okay? So that's the only idea. On the other hand, if you do baryogenesis, in principle, you can do as low as the scale of BBN, right? But leptogenesis you cannot do at that scale. You have to do it before electroic scale. Okay? So let me write down the Lagrangian, which we wrote earlier also for the type 1 seesaw. YD L bar H tilde NR plus half MR okay? So it gives you neutrino mass. From the seesaw, you make MR heavy, MD of the order of, so this is going to give you the MD. So you can do a seesaw that gives you the light neutrino mass, okay, which we discussed. So now, what we are proposing is that this NR not only solves the neutrino mass puzzle, but it also solves you the baryon asymmetry puzzle by going to L and Higgs. Higgs I am denoting as H1 to make it different from the Hubble, because I'll be using the Hubble also. Okay. So now how to calculate it? To calculate it is somewhat similar to the dark matter. So what you want? So you have to now, but the problem is that you have to solve two equations. One equation is for the NR, which is decaying, because you have to track the number density of the mother particle also. And you also have to track how much of lepton asymmetry you are producing. Okay? So that means you have to use two Boltzmann equations. First Boltzmann equation is very simple. It's like for the dark matter we have used for the freeze-in dark matter, for example. So let's write down. So dnr by dt is equal to the rate at which it is getting created or destroyed, nr going to lh, l bar h tilde h dagger plus rate at which lh1 l bar h1 is producing nr. Right? This is what we did yesterday. For the freeze-in dark matter, the rate of production minus rate of destruction is going to tell you whether how the number of this guy is actually changing. But yesterday, you remember, I ignored this term. I said that because there my interest was the A going to chi. So chi going to A I ignored because chi abundance was very small to begin with because it's a non-thermal dark matter. Here I cannot ignore it because L and H, these are standard model particles. They cannot be zero at the early universe. They are in equilibrium. They have a huge abundance. Okay, so I cannot ignore this. So I have to take both the term into account. So then, so rate of this term is very simple. So this I know that this is just the decay width of nr going to LH1, L bar H1 star multiplied by the n number density of, I'll just call it n. Okay, that's if I use it nr, I cannot use nr here. This is basically number, so yeah, that makes slightly the notation a bit messy. I should have used just n, but anyway, so you just keep in mind that this is just number, and this nr is the subscript is just for the particle. Okay, so this we found yesterday also, but this now we have to find, which we ignored yesterday. Okay, but now what is simple is that I can also write it that this is just equilibrium because L and H are in equilibrium, and in equilibrium this is equal to this provided I use N and R in equilibrium, right? This is the principle of detailed balance, okay, which we discussed. So I can write down this equation as simply as, so now I will put, so this I can write as NR equilibrium, NR going to LH1, L bar H1 star. Okay, so that helps me because I can take the, sorry, this is the decay width. So I can take this guy and this guy common, and inside the bracket I will just have NNR minus NNR equilibrium, right? So, and then I will write in terms of number density, N, I'll just call NN, A cube V naught, which I wrote yesterday also. So then I can write down this equation as dNN by dt plus 3HNN is equal to I'll just write gamma, which is basically the total decay width of n, and this is NN minus there will be minus NN equilibrium. This is the total decay width of n, which is the same thing as this. NR going to LH plus NR going to L bar H star. I can also write this thing in terms of co-moving number density, which I discussed yesterday, y equal to n by s. Then you can just do a few more steps and also convert t to x, which is mnr by t. Then you can write this equation as dyn by dx is equal to minus, I can also do a thermal average like we did yesterday. Okay. So what this term, so you can see that if yn is, so this also this equation is also very intuitive because if you say that okay, n is in equilibrium. So if n is in equilibrium, the co-moving number density cannot change because n is created and destroyed at the same rate. So whatever number of n you start with, it remains same. So that's why right hand side becomes 0. Okay? Only the number density will go down obviously because the universe is expanding, but the number does not change. That's what this equation means, right? Now we have to find out the other equation, which is a bit messy. We have to find out the lepton minus antilepton. That is what asymmetry means. So before going that, let's write the equation for leptons and antileptons separately. That is easy, and then take the difference. Okay. So by this same analogy, I can write down the equation for lepton. Left-hand side will always remain same because the number density always goes as 1 by a cube. So this will always remain same. Then how much it is produced. So this is like the equation for chi that I wrote yesterday. So it is produced from Nr. So decay width of Nr going to L multiplied by number density of Nr. Okay, this is what we did yesterday. I'm not writing a 2 factor here because only one L is produced from one Nr decay. Yesterday, A going to 2 chi, so that's why I wrote a factor 2 here. Here I'm not writing that, right? And then minus Nn equilibrium and this, okay? But there's a slight difference which I have to mention. Why I have written this term? So if I don't write this term, this equation is also fine at the beginning. At t equal to 0, when I start solving this equation, it is fine. But as time progresses, I am actually creating a difference between L and L bar. At t equal to 0, both L and L bar are same. They are actually the equilibrium number density of leptons. I don't distinguish. But as the Nr is decaying, you are creating an imbalance. So that's why it's better to keep track of this. Because in the next equation, I will write NL bar. And these two need not be same, right? Because you are creating an asymmetry by definition. So if I write down for NL bar, this is exactly the same equation. Only thing is that I'll just put the subscript different. And this is NR going to L bar, H1 star, and N minus NL bar. Okay, this is all right. So when I take the difference, so if I take the difference, I am actually tracking this number NL minus NL bar. Okay, so if I track this difference, then I will find, so this I will call say delta L. And you can write, since you know that there's a slight difference between NL and NL bar, you can actually write NL as NL equilibrium plus half N delta L, and NL bar, NL equilibrium minus half N delta L. You can write it like this, because then if you write NL minus NL bar, you just get N delta L, which is my definition. So you're saying that as time progresses, you are creating a slight imbalance, and that imbalance you are parameterizing as some plus and some minus. But initially at t equal to 0, there is no asymmetry, so they are in equilibrium, as expected, right? So now, if I write this equation, there are some steps which you can look at it. So then I write down my equation, n delta L n dt plus 3h n delta L is equal to epsilon. I'll define epsilon n minus half n delta L n equilibrium Okay, I get this equation after 2 steps. What is this asymmetry? Because if I subtract, I get this decay width minus this decay width. And these two decay widths have to be different because you want to create more lepton than anti-lepton. So if you say that this is and these are same, you are not creating any imbalance. So this difference is actually parameterized in terms of this epsilon. So this epsilon is the rate at which NR is going to LH1 minus NR going to L bar H1 star divided by total decay width of N. So this is known as the CP asymmetry parameter. So you need to have some non-zero CP asymmetry in order to create a delta L. Otherwise, you are not going to create it. Okay, so this is one of the requirements for leptogenesis. Now, just like I wrote the equation for N, I can also write the equation for in terms of y. And usually people write, because sphalerons act on b plus L, not b minus L, so people usually write this delta L as b minus L. So if I write this as b minus L, I just have to, because I'm introducing a minus sign in front of the lepton, so I have to put a minus sign here also. Here I don't need, because I have already a minus sign inside b minus L. Okay, so this is my equation. So I can write down this equation in terms of the y, dy b minus L dx, then this is epsilon d yn minus yn equilibrium minus, so this is just a useful parameterization. So let me define these quantities. Epsilon I have already defined. So d is the decay width thermal average divided by hx, and this thermal average I told you earlier you can write down as the zero temperature decay width multiplied by this k1x by k2x, which are modified Bessel functions. So this is just 2x, and this WID is just half inverse decay width divided by hx, and inverse decay width is actually related to the decay width just by yn equilibrium divided by yl equilibrium. So the inverse decay width means L and H going to N. The forward decay width is N going to LH. Okay, so they are different just by this. It's just again you use the detail balance. In equilibrium, both the processes are same, so that's why both are coming here. Okay, so but you don't have to worry about all this. This is just a useful way. If you look at any books or papers, you will find that they will not write all these messy things. They will write all these things here. So what does it mean? Why we use the word W is because it wash out. It has a significance. What it tries to do, you see here, B minus L. So this term is responsible for creating the B minus L, right? But this term is trying to wash it out. That means whatever you are producing, it is going to wash out. That means you are producing N going to LH, and you have an imbalance of L and L bar. But if L and H are going back to N again, that's what this inverse decay tells you. You are losing the asymmetry, right? That's the problem. So this will try to reduce it. So now if you solve these two equations numerically, what you will find? You will find that, let's start with the right-handed neutrino to be in equilibrium. So so that means Yn x. So this will just follow the equilibrium distribution which I discussed yesterday for the WIMP. It'll just go like this. Because it decays, it is not WIMP, it is not stable, it doesn't have to be there in the late time, so it will just go decay and just disappear from the universe, which is fine. But in the process of disappearing, it should produce the asymmetry. That is a requirement. So then you solve for the YB minus L also. So if you solve for YB minus L, you find that it will actually grow. It will grow, but it can, sometimes it grows, and sometimes it can grow and then slightly go down also. Why slightly goes down? It increases, then it can go down also if this term is large. And you see, this term is actually combined with the B minus L. That means this term will be important only when you produce sufficient number of B minus L already, or sufficient number of lepton asymmetry already. Initially, this is 0 because YB minus L is 0 initially, right? So if you produce, so this is trying to, so you are creating asymmetry, but this inverse decay is also trying to make it small. But at some point, since the universe is always expanding, all these rates will fall below the rate of expansion of the universe, so it will actually saturate. So what you have to worry about is whether the final B minus L is sufficient to produce the observed eta B, which is of the order of 10 to the power minus 10, which I mentioned, right? So how to do that? So for that, one has to use a conversion factor, which tells you how much of lepton asymmetry is actually converted into baryon asymmetry. Okay, and also this is thermal leptogenesis. So here I have assumed that N was in equilibrium in the early universe, but it is not important. You can say, okay, N is not in equilibrium. I have just produced it like a FIMP. Then what will happen? It will grow. It'll grow and will reach the equilibrium. And then it will follow like this. This is also fine. It'll give you the same thing. It'll give you slightly different behavior here. So here we are plotting yb minus L absolute. So if you plot it for this case, it's just very simple differential equation. You can solve it in Mathematica by putting some numerical values of these quantities in the front. You will find that this will go like this, and then it has a sharp fall, and it goes like this. This is for the case where this guy was not in equilibrium initially, and this is precisely because if you look at the equations, what happens that yn, what you are assuming here is that yn was 0 initially. Then what happens, this term has a negative sign, because yn equilibrium is not 0, it is a large number. Now, as yn is increasing, at some point this term will become 0, and after that yn will rise above, say, y equilibrium, so this will change the sign. So if you change the sign, you see the dip. Okay, it changes the dip. So if you don't plot this, what you will find is that it actually goes like this. Now, if you put absolute value, this will actually go up, flip it. So then it gives you a fake kind of impression that there is something like a resonance, but there is no resonance here. So if you look at the leptogenesis papers and get puzzled by this kind of behavior, which looks like a resonance in particle physics, it's not resonance. It's just because they are plotting absolute value of the B minus L. Okay. Anyway, so all these things are not very important because they are anyway going to produce the final asymmetry. So once you know, so what you are solving is yb minus L. So if you find out the final value of yb minus L at x very large, which is the 0 temperature, then you can find out yb is equal to some factor called Sphaleron factor, and the Sphaleron factor is given as 8nf plus 4 nh1 divided by 22nf plus 13 nh1. So the Sphaleron factor depends upon how many generation of fermions you have and how many Higgs you have. So if you put nf equal to 3 and nh equal to 1, you will get this to be 28 by 79. So this tells you how much of B minus L asymmetry you actually require to create YB. And this YB you can convert to eta B, because if you know the entropy density in the present universe, because we know the temperature, okay? So you can find out eta B also. So eta B you can find out at recombination, which is coming from CMB, around 3 by 4 C Sphaleron by F epsilon KF. So analytically, people try to estimate it like this. So epsilon is the same epsilon CP asymmetry parameter. So as I said, you need non-zero value of epsilon to get asymmetry. This is something called efficiency, which will depend upon the detail of the washout. That means how much of CP asymmetry you are actually converting into the final asymmetry, because there will be washouts. If you have very high washout, then the efficiency will be small, because it will try to erase the asymmetry that you are producing. F is the dilution factor, because you are creating asymmetry at temperature equal to, say, 100 GeV or even more, but recombination is happening at a temperature of electron volts. So there is a difference in the entropies in these two temperatures, so that will give you this F. So you can actually find it out and actually find how much of CP asymmetry you require to create the asymmetry that you want. Okay. So finally, what is important, another important thing is that how to make sure that you have a non-zero CP asymmetry. Okay. If you calculate, so this is simple QFT. So if you have this n going to L H1, and you create n going to L bar, you actually calculate this process. So this process will be, say, this is Yukawa 1. How this decay will look like? This decay will look like y1 mod square, some phase space of, say, I1. This will look like y1 again, mod square, some phase space, I1, this I1 bar. Particle, antiparticle, is that going to matter for I1 and I1 bar? Particle, antiparticle have same mass, not going to be important. So that means if you only calculate 3-level processes, CP asymmetry is 0. So you have to go beyond the 3-level, okay? So that makes the calculation of CP asymmetry a bit complicated, but I have given a toy example in the notes which you can look at, which actually tells you a few important things, that what actually guarantees that you can create. That means if you want to build a model, what actually guarantees that you can actually generate a non-zero CP asymmetry. For example, in the type 1 seesaw, if you have only one right-handed neutrino, you cannot produce non-zero CP asymmetry. You need at least two. Okay? And that is actually good for us, because for neutrino mass also I need at least two. If I have only one right-handed neutrino, I will get only one neutrino mass, but I need to have m solar, m atmospheric. So everything fits perfectly. It's just like a nice coincidence, okay? So you can calculate this toy example, which is also given in Colburn-Turner's book. I have also given it here. You can look at it. So this actually tells you that to have non-zero, you need at least two right-handed neutrinos, because you cannot create it at tree level. So you have to go to one loop. At one loop, so this is say tree level. At one loop, what kind of diagram you have? You can have, so this is say N1 LH. Let's say N1. You can have a loop like this, LH1, and then you can have N2, and you go to LH1. So this is like a self-energy correction. You cannot put N1 here, because that is not physical. That will not give you a new physical process, right? Again, you can have N1. You can have a vertex correction. These are the only diagrams you can have at one loop. So you calculate this plus this is self-energy, this is vertex, and you will find the expression for CP asymmetry. Okay? So it will depend, and there's one more thing, is that these loops, the particles that you have, they should be on shell. So loop particles has to be on shell. And this comes because if you calculate, say, this process, this is a toy example, let's say. This process, you can put some coupling here, whatever we want, Z or whatever, ZI is, ZI. I can be different, I have to be different actually here, 1, 2, 3, 4, whatever. You'll find that this difference for the particle A going, so this is the A going to XX, A going to XX. So if you find out this going to XX minus A bar going to X bar by taking this plus this contribution, that means you add the amplitudes, then take mod square, then take the difference of this process and this process, okay? And you will find that this is actually proportional to something like, let's forget about the numerical factor, imaginary part of some coupling, ZI, ZJ, GK, ZL, some stars will be coming, which tells you that the coupling should have some CP phase. That means there is some CP violation, which is obvious from our CKM. That's why we call those phases as CP violating phases. The imaginary part will take out those phases. So you need phases in the Yukawa couplings, which is understood, but you also need something called imaginary part of something like Fx. And this part is coming from the phase space plus the loop integrals. And if you use something called, there's something called optical theorem in QFT. If you use it, you find that if you take any diagram, you want to take out the imaginary part of that diagram, then it tells you that whatever particles you are taking, for example, you take this diagram, if you want to find out the imaginary part, this is equal to this, like take all, and then you take those all going back to this, and sum over this. And this is possible only when these guys are energetically possible. I mean, these are on shell, okay? So that's why if you put some heavy guys here, it is not going to give you this part imaginary, okay? So this has to be actually satisfied, and which is absolutely fine as far as type 1 seesaw is concerned, because these guys are anyway much heavier compared to LNH. Okay, so these are the requirements which will actually help you to get. Another important thing is that if you are using now N2, N1. So these are second. Third one is that MN1 cannot be exactly equal to MN2. If it is exactly equal, what will happen is that you have both N1 and N2 at the same temperature because they have the same mass, so their abundance will be exactly same, at least the equilibrium abundance. So you are producing asymmetry from N1 decay also, N2 decay also, and they will exactly cancel out. Cancel out because they have the same couplings in the loop diagrams. Okay, so that's why it's not. So you need to make sure that N2 is heavier, N1 is lighter, and only the contribution of the lighter one is important as far as leptogenesis is concerned. Heavier one, it can produce at very high temperatures, but there are washout processes going on at low scales. So that will anyway wash it out. Because LH may not be able to go back to N2 because N2 is heavy, but LH can always go to N1. N1 is lighter. So whatever asymmetry N2 or maybe N3 might have produced at high temperature, not important as long as you have the lightest guy N1 producing sufficient asymmetry at low scales. Okay, so there are some other things like what should be the seesaw scale, because type 1 seesaw, all these Yukawas as well as the mass of right-handed neutrino, they are related to the neutrino mass, because I know that neutrino mass is Yukawa square, Higgs-Webb square, which is V square by mr. So I cannot choose them whatever I want. Okay, so if my N1 and N2, their masses are very much separate, that means they are hierarchical, I can find the bound because I know how much of epsilon I need to produce the eta b. That should be of the order of 10 to the power minus 7 or minus 8. If I want to do that, I will get an upper bound, lower bound on the scale of mr. Okay, because CP asymmetry function will depend upon this mr also. Okay, which I have given in the notes. I don't have time to go into the details here, but if you have any questions, I will take tomorrow on that part. So it gives you a bound on M1 more than 10 to the power 9 GeV, which is called Debasish Borah bound. So this actually tells you that leptogenesis is a very high scale phenomena, which is out of reach from all our terrestrial experiments, but you can actually enhance it if you have something called resonance. So this bound is valid if N1 and N2, they are hierarchical. N2 is, say, 10 times, 100 times heavier compared to N1. But if you say that they are very much degenerate, that means MN1, N2 minus MN1 is of the order of the decay width of N1 divided by 2 to be precise, then what will happen is that in the CP asymmetry expression, especially for the self-energy diagram, you will find that there is a resonant enhancement. That means even if you choose M1 smaller, what happens if you choose M1 smaller? The Yukawas become smaller because this has to be sub-electron volt. So what happens is that if you choose M1 smaller, your Yukawa becomes smaller, but even then you can produce a large epsilon by something called resonant enhancement, because the CP asymmetry formula, which I have given in the notes, you will find that there's a denominator, there's something like Mn1 minus Mn2. So if you put it equal, you get a huge resonance enhancement. So you can produce order 1 CP asymmetry even with small TeV scale Mn1, provided you make it very degenerate, which is a bit fine-tuning because you have a TeV scale right-handed neutrino, you want another one which mass splitting of the order of kilo electron volt, which is a bit fine-tuning because TeV and keV, which is like 10 to the power 9, right? This is a bit fine-tuning, but it actually works. So people actually work on those ideas also, because the good thing is that it gives you low-scale leptogenesis, which you may be able to probe in some experiments. How to probe other leptogenesis? Especially if you have high scale, there are some ways to probe this high-scale leptogenesis by gravitational wave experiments. Okay, those are of course indirect evidence, not direct evidence. I will talk about some of those tomorrow. And you can also include, you can also have leptogenesis with first-order phase transition. Okay, first-order phase transition can help you to achieve leptogenesis in certain ways. Okay, I have given some reference here, some notes here. which you can look at. If you have questions, I will take tomorrow. And advantage of those scenarios is that if you have a first order phase transition, you have bubbles will collide and they will produce you gravitational waves. Okay, so that's one complementarity. But all these are, these are all indirect evidence. It's very difficult to probe leptogenesis or baryogenesis directly. You want to see a particle in your lab, and you want to confirm that it is decaying more into particle, less into antiparticles. Extremely difficult job because of so many constraints on lepton number violation, neutrino mass. If you do direct baryogenesis, there will be constraints from proton decay because proton lifetime is 10 to the 34 years. So if you want to have a baryon number violating signatures in the colliders, there will be strong bounce from the proton decay. Okay, so that is also another problem. So I will end here. If you have any questions, I'll take. Thank you.
Thank you so much for the speaker. We have questions here? Questions? Okay, thank you so much for the nice lecture. Thank to the speaker.